Hello everybody and welcome to the MMA Training Bible's Guide to Generating Muscle Force. I'm Dr. Jason Gillis. Now, in this video lecture, I'm going to be talking to you about how muscles generate force. There's really two big things that I want you to get out of this video. Two things we're going to cover. First thing, we're going to cover the different types of muscle contraction. And after that, we're going to talk about the 4 factors that influence muscle force generation. So without further ado, let's get right into it. So first things first, there's 2 types of muscle contractions that I want you to be aware of. One type, it's called static contraction, or you may have heard a similar term, it's called isometric contraction. Both of those things, for us, it means the same thing. Static or isometric, same thing. The other type of contraction, it's called a dynamic contraction. So let's first start by talking about what a static or isometric contraction is. So during a static or isometric contraction, your muscle, it does produce force, but the length doesn't change in the joints. So this is pretty important because this is really the key characteristic. There's no change in the length of the muscle or in the angle of the joint. And what you're getting here is force development, but if you remember back to previous videos, we talked about myosin cross bridges and how they move across actin myofilaments to cause movement in the muscle. That doesn't happen. There's no sliding here. So that's one type of contraction, the static isometric contraction. And if you want to think about that or visualize it, think about maybe when someone's trying to armbar you and your arm is stretched out and they're on top of you, they're about to stretch your arm out, but they're just pulling on you and you're pulling in the opposite direction. They're trying to strengthen or stretch your arm out, but you're not going to let them. So the arm position, it isn't moving, but it's producing force. So that's a good example of a static isometric contraction. Another way to think about it is maybe if you're in a push-up position and you're holding yourself halfway up, or maybe if you're in a chin-up position, you're holding yourself halfway up. There's no change, there's no movement, there's no change in muscle length, there's no change in joint angle. You're just engaging in that contraction, but there's no change in movement. The other type of contraction that I want to contrast that with is called a dynamic contraction. And that's when your muscle produces force and it changes in length. So in this case, the joint is going to be moving. And here, an example here is, let's go back to that arm bar example where you're on your back, someone's trying to stretch you out, stretch your arm out, and you generate enough force to pull your arm back into your body to save it. Or another type of dynamic contraction is maybe you don't win that battle. Maybe your arm stretches out and your opponent stretches your arm out and you got to tap out or else break your arm. So that's a dynamic contraction when your arm is producing force and your muscle length is changing and your joint angle is changing. And there are 2 different types of dynamic muscle contractions, and I kind of alluded to them there depending upon which way the arm bar goes. And I want to review both of those next. Okay, let's talk about that first type of dynamic contraction, because remember, we got static contractions, we got dynamic contractions. The 2 types of dynamic contractions are shown here. We got concentric contractions and what are called eccentric contractions. Big terms, but let's unpack them so you understand exactly what they mean. A concentric contraction, that's when your muscle is generating force and the muscle itself is shortening. This is probably the most common type of contraction. And if you think back to previous videos when we talked about the sarcomere or the myofilaments, ultimately what's happening is your whole sarcomere is shortening. It's getting smaller and getting a little bit fatter because the muscle itself is shortening. So let's go back to that arm bar example. A concentric contraction, if you can picture yourself laying on your back, someone's trying to stretch out your arm, they're on top of you, and your arm is bent and they're trying to pull it and stretch you out while you're trying to pull your hand closer to your body to prevent that arm bar from going off. So in the situation where you're pulling on your arm and they're pulling on your arm, but your arm gets closer to you, so you're saving yourself from the arm bar, then that is a concentric contraction. So let's talk about the eccentric contraction. An eccentric contraction is also when your muscle is generating force, but your muscle is lengthening. So if you could picture those microscopic structures, the cross bridge, the sarcomere, it's all getting longer. An example, maybe you're lowering heavy weight. But continuing with the example that we've been using, you're in that armbar position and you and your opponent are both fighting for that arm. You're trying to pull it towards you, and if you do, then that's a concentric contraction. Your hand gets closer to your body and you save your arm. You can escape from that armbar. When your opponent is able to stretch your arm out and you're still flexing as hard as you can, but despite your flex, they've got the technique, they've got the force, they can generate more force in you. That's going to cause your hand to go farther away from your body. They're going to lengthen out your joint, and that is specifically called an eccentric contraction. When you're generating force and your hand is getting farther from your body, they're able to stretch out that arm, they're able to increase the joint angle, the muscle lengthens. That is an eccentric contraction. So those are the two types of dynamic contractions. Pretty simple. Let's go and move on to the next phase of this video lecture. So what determines how much force we can generate when we're in that armbar position, when someone is trying to armbar us and we're on our back? What determines how much force that our muscles can actually generate? Well, there's 4 factors that determine that, and I want to review each of those in turn. The first factor that we're going to look at is called motor unit recruitment, and I'll familiarize you with this again just very briefly, but we did cover this concept in a previous video. The next concept that I want to talk about, the next factor that can influence muscle force generation, is called rate coding, and it's the frequency of stimulation. Probably never heard of that before, but we'll introduce it to you. Another factor, it's called the length-tension relationship, and that very much relates to that armbar example that we were just talking about, and we'll bring it back to that. And then the final factor that I want to talk about is the speed-force relationship, and that's going to draw upon your understanding of those concentric and eccentric contractions. So if you didn't get that, go back now and re-watch that and make sure that you understand the difference between a concentric and an eccentric contraction. Very briefly, a concentric contraction, an example might be when you're curling a dumbbell up towards your body in like a bicep curl, and then an eccentric contraction would be when that dumbbell is moving away from you. We use the armbar example where a concentric is where you're saving yourself from the armbar, and an eccentric is where your arm is lengthening and you're getting armbarred. So let's talk about the first component, motor unit recruitment. So the first thing that we're going to talk about, it's motor unit recruitment. And before we get too far into this, I just want to remind you what a motor unit is. So let's have a look here. If you should be familiar with the fact that I like to draw pictures here. So what we're going to draw is a motor unit. So first we're going to start, let's see here. I know it's looking pretty horrible, but hopefully it'll come out correct. Feel free to draw along. There we go. So what we're drawing here, and basically what we're looking at, this is a neuron that we're drawing here. And if you've seen previous videos, or maybe you've taken an anatomy course or physiology course, you may recognize some of these structures here. So this is a neuron, and information moves from here down that way, and what we have down at the end here, we have the neuron that connects to something. And I'm sure that you can imagine what this is going to be. This is going to be muscles. Let's draw another muscle there. Whoops, bring it back here. There we go. Okay, so what we're looking at here, bring this up a little bit. We're looking at muscle fibers here and all the little structures that are inside of them. Okay, so this is a motor unit, and we have the cell body of the neuron up here, and then we have what's called the axon helix, and then we have action potentials, which are signals. This is how the nervous system communicates. We have signals that move from the cell body all the way down to the axon terminal, and the axon terminal is at the very end down here. And what we're looking at here, these are muscle fibers. These are actually myofibrils. And this whole structure, when we put together the neuron with all of the muscle fibers that it innervates, it's called a motor unit. So one of the factors, let's go back to that presentation now. So now that we know what a motor unit is. So motor unit recruitment is going to influence how much force that we can generate. And if you recall from previous videos, we talked about different types of motor units, different types of muscle fibers. A type 2 motor unit is going to be associated with type 2 muscle fibers, which are going to be capable of generating more force than type 1 muscle fibers and type 1 motor units. So some of the differences that you're going to see there between type 1 and type 2, if we go back to that little picture, a type 1 motor unit is going to be smaller in diameter, so it's not going to be able to conduct action potentials as rapidly down the neuron. And a type 1 motor unit is going to have less muscle fibers attached to it than a type 2 motor unit. So doesn't it make sense that the motor unit that has more muscle fibers attached to it is going to be able to generate more force? I hope that's pretty clear to you guys. So again here, fewer muscle fibers versus more muscle fibers, that's really what's determining how much force that our muscles can generate. Let's continue on and talk about another factor. So we talked about how neurons really transmit electrical signals from the cell body down to the muscle fibers, and that causes them to activate. Now let's talk about that maybe just in a little more detail. Now, because the second factor that we want to talk about directly links with that is called the frequency of neural stimulation. So essentially what we're talking about, if we go back to that little picture, we've got our neuron that's sending signals down. The frequency that it sends signals down here determines how much force these fibers can generate. So if it sends, let's say, one signal down here, it's going to cause a little twitch in these muscle fibers, and that's going to generate a little bit of force. So you can see here a single stimulus causes the muscles to twitch and generate some force, and that's called a twitch. When you have multiple signals moving down that neuron, it's going to cause a couple twitches, and it can generate a little bit more force than a single twitch. So more stimuli coming down that neuron, it equals more force, because essentially what you're doing is you're summing the forces of all those individual stimuli, and that's why we call this summation. And then the last one that I want to talk about, it's when you have lots and lots and lots of stimuli moving down that axon, and it causes lots and lots and lots of twitches in those muscle fibers, and that's called tetanus. So what I want to do now is I just want to draw you a little picture of what that actually looks like. So let's go back to our drawing board over here. Let's move over, make some room. Okay. So let's draw a little figure here. There's going to be the vertical axis, and then let's draw a really long horizontal axis over here. There we go. Okay. So what I want to draw on this axis here, it's going to be, let's call it tension. So that's called tension. And so what we're seeing up here is tension gets higher up top, and tension is going to be really low. Let's call it 0 down here. And on the horizontal scale, let's call this one the frequency of stimulation. So actually maybe we'll just call it time. Whoops, move it up here a little bit. Time. Okay, so the first thing that we said is when you have one signal or one stimulus moving down that neuron, down the axon toward the muscle fiber, then you end up getting a twitch. So let's just draw that. Let's say we've got one stimulus happening right there, and let's use S as stimulus. What's going to happen is we're going to see an increase in tension in the muscle, and then it's going to go back down to normal. Okay? And that one is going to be called a twitch. Sorry for my horrible writing here. So that's going to be called a twitch. And then what's the next thing that can happen? The next thing that we talked about, it was called summation. So let's say that we had another stimulus here, and then another stimulus here, and then another stimulus here. What is that going to look like? Well, we said what happens when you have one twitch, you see an increase in tension, so that's an increase in tension to there on the tension scale. And then when we get these stimuli in very close proximity to each other, then what will happen is they'll start to kind of build up a little bit. So let's show you. After one stimulus, then it'll go up and then it'll start to decay. But then what will happen is if we get another stimulus here, it'll jump up again, same characteristic, same waveform, but then it'll start to decay a little bit. And then before it goes all the way back to normal, if we have another stimulus, it shoots all the way back up. And so what you end up getting, and then it'll start to decay if you don't get another stimulus. So this constant increasing stimuli, this is called summation. All right, so we're still, essentially the difference is we're not allowing enough time for the stimulus to decay, and we hit it again with another stimulus, and so it causes an increase in stimulation. And then the last thing that we talked about is what happens if we have a whole bunch of stimuli in like a really short period of time, right? What's going to happen if they came that close? Because here, you see how far they were separated, and it still causes a little increase. And if there's a really long separation between here to here, the stimulus is probably going to die out. You're not going to get a lot of tension. So see what happened with the amount of tension we got here. It probably increased to here. So we're seeing this increase with one twitch, tension to here. When we have summation, tension increases up to here. But what happens when we get this here? What happens when we get all of these stimuli in a very short period of time? Well, I think that you're going to be able to predict what happens here. It's going to decay a little bit, but then it's going to shoot up, and it's going to reach this maximum. And you can see now we're generating the most force out of any of those characteristics, out of any of those coding patterns. So the frequency of stimulation, or the rate coding as we call it, is going to cause a change in the tension in the muscle. So if you have one small stimulus, is going to cause a twitch in the muscle. Many stimuli, it's going to cause summation. And then if you have a lot of stimuli in a very short period of time, that's referred to as tetanus. So T-T-A-N-U-S. Horrible writing, but that's fine. I hope you get the points. So this is an example of frequency of stimulation, and some people call it rate coding. Okay. All right, let's move on. Let's move back to that PowerPoint presentation. Okay, so what's another factor that can influence how much force our muscles can generate? Well, that third factor that we mentioned at the beginning is called the length-tension relationship. And if you remember, we talked about sarcomeres. And sarcomeres are really the smallest contractile unit in a muscle. And it turns out that there is an optimal sarcomere length, or an optimal overlap, that can maximize your force production. If it's too short, or if the sarcomere is too contracted, or if your arm is too contracted, let's say, or if it's too stretched out, you're not going to be able to generate much force. It turns out that there is an optimal overlap in the sarcomere where you can generate the most force. If it's not stretched out enough, or if it's stretched out way too much, then you're going to generate little force. So what I want to do is give you a little diagram to show you this concept. Okay, so let's do a little drawing here. Let's start off with the vertical axis. Whoops. There we go. Little vertical axis. And then let's draw a horizontal axis. And this scale over here, this is going to be tension. So tension is going to be building up here to its maximum, and down here tension is going to be 0. And on the other scale, let's say that this is going to be the sarcomere length. Sarcomere length, okay? So let's say right here, let's draw the association between sarcomere length and tension. It's going to look something like that. Let's try to tease this out for you here. So over here, the sarcomere length, it's going to be very short. So this is kind of like the muscle in the fully contracted state right here. And over here, the muscle is going to be in the fully extended state over here. So just to make this a little bit easier, let's give it some numbers here. Let's say that this is going to be, say, position 1. Let's say that this is going to be position 2. Let's say that this is going to be position 3. Let's say that this is going to be position 4. And this is going to be right here, position 5. Okay? Now what I want to do is I just want to draw some sarcomeres over here that relate to those positions, and then we're going to walk our way through this figure here. So let's first draw what the sarcomere is going to look like right here, so right over there. So let's draw that sarcomere. So that was actin we just drew, and this is myosin in the center, and these are the Z discs. Okay, so what we're seeing here is this is an example of a sarcomere that's very stretched out, and there's not a lot of overlap between actin and myosin. And that is going to be associated with a very small amount of force. So this is the example of when your arm is totally outstretched in that armbar position. This is when you're getting armbarred. And so you see, once you move down to this position, your arm is stretched out, you know that you don't have much of a chance to move, and you're not very strong in that position. So the next thing I want to draw is position number 2. So that's going to be right here. Let's draw what that one is going to look like. So that was actin. Let's draw myosin here. Now we're drawing actin again. And so what we're looking at here is this sarcomere is going to be a little more shortened. And so you're going to see more overlap here. And this relates to this position up here. And so maybe this is the position where you have a little bit of a bend in your arm. Maybe you're at 90 degrees or so. The point that I'm trying to make, though, is that as your arm moves up from being totally stretched out, there's going to be more overlap between actin and myosin, and you're going to be able to generate more force as a result of that. Because remember, we're looking at this tension relationship here, and there's a small amount of tension over here, and there's a whole lot of tension up here. So we want to be up here if we want to generate a lot of force. And then let's draw another picture associated with number 3. So we're going to draw that sarcomere length. So maybe we're going to see a little more overlap. We're going to see an even shorter sarcomere. A lot of overlap here with the myosin. Let's draw those actin and the structures that hold them together. So again, we're seeing an even shortened sarcomere here, a lot more overlap, and that's going to allow us to generate even more force right over here. So you can see, well, actually, you know what? It's kind of the same, isn't it? It's not a huge difference there. That's because there's a lot of overlap. Let's continue on down. Let's draw the structures of the sarcomere with actin and then myosin. This is structure number 4 here we're looking at. And what we're seeing is a lot of overlap here. Look at all that overlap. And what we're starting to see at position number 4 is, as a result of the increasing overlap, we're seeing, let's say 4 is right there. It's going to be a reduction in tension. So we're moving from up here down to here. And so the more overlap we have, the less tension we're going to have. And let's finally draw a picture of number 5 to give you a complete picture here. Complete overlap. And let's draw those myosin structures. There you go. So what we're looking at here is we have complete overlap. And that is going to be represented by number 5 over here. And we're seeing a very small amount of tension. So if we wanted to label these, then we can start off up here with 1. This is number 2, number 3, number 4, and number 5. So what I want you to understand from this figure is there is an optimal sarcomere length. If you want to generate the most force, you're going to be somewhere around here, around 2 and 3. So there's not full overlap between actin and myosin here. And I guess the main point is, despite what you may have thought, when your muscle is fully contracted, over here in 5, and when your muscle is fully extended, you really can't generate much force at all. Okay, let's talk about the last factor here. And the last factor is factor number 4. It's the speed-force relationship. And so I mentioned before that when we're talking about this factor, you've got to have a good understanding of what a concentric and an eccentric muscle contraction is. So remember, a concentric contraction, that's when your muscle is shortening, like when you're doing a bicep curl and you're lifting the weight, or when you're in that armbar position and your hand is coming closer to your body and you're getting out of the armbar. Essentially, you're increasing your safety. And during an eccentric contraction, that's maybe when you're lowering the weight during that bicep curl or when your arm is being stretched out. Either way, you're providing force. So there is a relationship between the speed that you're moving during those concentric contractions or the eccentric contractions and how much force you can actually generate in the muscle. Now, this is going to seem kind of counterintuitive to you, but we'll try to walk you through it and explain it. During a concentric contraction, let's use the example of a bicep curl. What you start to see is maximal force development. It decreases at higher speed. So the faster that you're moving through that bicep curl, you're going to see a slower, or rather a lower maximal force development. When you're moving really, really fast during that bicep curl, less force is being developed. Now, in total contrast to that, during an eccentric contraction, so let's say you're starting at the top of that bicep curl, the faster you move during an eccentric contraction from the top to the bottom, let's say, you're going to see an increase muscle force development. Now, this is going to seem a little confusing, but I've got a little figure. We're going to draw a little figure to try to explain this to you. Okay, so let's again draw a little figure here, and let's start by drawing the vertical axis right there, and then let's draw a horizontal axis right here. Okay, so let's go over here and let's say that the vertical axis is going to be force. So we're going to have a high degree of force up here, and let's say we're going to have a very low degree of force down there. And let's say on this scale, let's call it speed, or let's call it velocity. This is going to be velocity. And let's make this even more confusing for you. And let's say that this is 0, okay? Velocity is 0. So we're going to see increasing velocity in that direction, and we're going to see increasing velocity from 0 out in that direction. So why have I done this? Why have I done this? Well, let's see if we can explain it. I'm going to put another little line right up here. Okay. So again, this line that I've just made in the center, this is going to represent force as well. So we're going to have a high degree of force up here and then a low degree of force down here. So both of these scales are kind of the same. So let's say that force is force. Okay? So the first thing that I want to do is I want to show you what happens when we're generating, when we're moving through a concentric contraction. So let's start right here. So this is going to be an example of a shortening, or also called concentric. Okay, so an example of a shortening concentric contraction is when you're raising a dumbbell, when you're doing a curl, for example. So let's show you what happens to force as velocity changes. So we're just going to draw a little figure here. Okay, so what we've done is we've drawn what happens to force when you're moving through that bicep contraction. So let's say that this is a very high speed right here, and then this is a very low speed, right here. So that's what we said down here. Velocity is 0, and then we keep on moving faster and faster and faster. So this is kind of like the halfway point right there, where we're kind of moving a little bit fast. So what this tells us is that we're able to generate the most force during a concentric contraction when we're moving very, very slowly, right? Right here, when we're moving very, very slowly, we're able to generate a whole lot of force, right? Because force is higher up here than it is down here, right? Force is 0 here. So when we're moving slowly during we're doing a slow bicep curl, we can actually lift an awful lot. And think about that in the gym. I'm sure that you can, if it doesn't matter how much time it takes you to lift that bicep curl, to lift that dumbbell, you're going to be able to generate a lot of force and you're going to be able to lift that weight. But if I said, okay, you got to double the speed, you got to lift that same dumbbell as fast as you possibly can, or double that speed, you're not going to be able to. You're going to have to lower the weight. So what happens is, if you want to increase the speed, maybe down to here, you're going to have to see a reduction in force. So the faster that you move, let's say if you double the speed from here to here, then you're going to see a halving of the force. So what you see is as you start to move faster, as you start to move that dumbbell faster, then you can't generate as much force. And again, as you start to approach your maximal velocity that you can move, then you're not going to be able to generate much force at all. So you can see that right over here. A very small amount of force. Again, it decreases even further. So I hope this is clear. During a concentric contraction like a bicep curl, the faster you move, the less force that you can generate. So the reason why I split this figure in two is because on this side we want to talk about eccentric contraction. So remember, an eccentric contraction is when you're generating force, but you're not generating enough force to actually shorten the muscle. Your arm is actually lengthening. So think of the example of maybe you've been in the gym and some of your friends, they help you get the dumbbell up to the top and then you slowly lower it. And you're trying to fight it off, you're trying to raise it, but you can't, it's too heavy. So you're slowly lowering it. So what I want to show you is what happens to force during eccentric contraction. So let's draw that figure. So what we're looking at here is, again, this is 0 velocity and this is increasing velocity during eccentric contraction. So this is when you're at the top of that bicep curl with that really, really heavy weight and you're increasing the speed that you're dropping it. This is what we're seeing here, increasing speed this way. So again, we're looking at force here. The force axis hasn't changed. High force is still at the top and low force is still at the bottom. So what we're seeing here is when velocity is 0, whether it's, well, obviously it's not going to be an eccentric or concentric contraction. This is actually an isometric contraction. Then you're going to be able to generate a good amount of force. But as you increase the speed, let's say you increase the speed to, say you double the speed to here, then what's going to happen to force during an eccentric contraction? Well, you're going to see an increase in force. And again, as you increase the speed of this eccentric contraction even further, you're going to see an even greater increase in force. So the moral of this story is, if you want to generate the most force in your muscle, it's going to be during eccentric contractions when you are trying to generate muscle force, but that muscle is lengthening. And some people think that that's because it takes more energy to rip those sarcomeres apart, those attachments from the myosin to actin myofilaments. It takes a lot of energy to just break those and rip them apart, because that's really what's happening. Okay, so let's finish off this video lecture here. I want to give you a little summary. So this is a summary of what we talked about. There are two types of muscle contractions that you need to know about. There's isometric and there's dynamic. And there are further two types of dynamic contractions. There's concentric and then there's eccentric. And the next thing we cover, there's 4 factors that influence how much force your muscle can generate. The first factor we talked about, motor unit recruitment. The next factor, the frequency of neural stimulation or rate coding. The next factor, the length-tension relationship. And the last factor we just finished talking about was the speed-force relationship. So that's all I wanted to cover in this video. If you're interested in more videos and articles, please visit the MMAtrainingbible.com. You can read about me and my background here, my education and my training and all that stuff. You can pause the video and check that out. You can also see that online as well. So that is it for this lecture. I hope you got something out of it, and make sure you go back and check out all of the content that we have, share it with your training partners, and I will see you next time.